So in this video, we are looking at introducing a couple of new graphs to do with powers, polynomials, and circles. Now, we talked about polynomials in the previous video, so we're going to be looking at a couple of different types of graphs here. Some of them we've seen before on this channel, some of them are new. Now, we're going to go through, sketch these using a table of values just to see how they behave, and then just get a general picture of the graph. Now, the first one here is y equals to the square root of x. So if you substitute different values of x into here, we will notice something happening. Now, we know that if we put a negative number under the square root, then we're not going to get a solution. We're not going to get a real solution. So the calculator is just going to tell you math error. So basically the number that we have to start at, the first number that will generate a real y value is 0, because if you take the square root of 0, it just gives you 0 back. Now I'm going to go through, because I've done all of these, have a go pause and substitute these into the rule and see what you get for y. But when I take the square root of a quarter, I get a half. When I take the square root of 1, I get 1. When I take the square root of 2, I get root 2. And when I take the square root of 4, I get 2. So drawing this in, we're just going to substitute these coordinates in. So when x is 0, y is 0. When x is a quarter, y is a half. So that's about here. When x is 1, y is 1. When x is 4, y is 2. And when x is 2, y is root 2. So that's going to be roughly there. So what you're going to notice is when we draw this, you will see this particular curve. This is our curve of y equals to the square root of x. Now we can see that pretty clearly it's never going to, based on the numbers we're substituting in, there's no negative x values here. So the domain is x is greater than or equal to 1. And the range is also y is greater than, domain was x is greater than or equal to 0, because from 0 onwards, the graph exists. And that's the same in the y direction as well. So for these values, when we substitute them in, we'll never get a negative output of y. So this will just continue going up as you see here. Next one we're looking at is cubics. So we have talked about these before, but just a little bit of a recap. Substituting this into our table of values, when x is negative 2, y is negative 8, we get negative 1, negative 1 over 8 here. We get 0, positive 1 over 8, positive 1, and positive 8. So writing these values in, when x is negative 2, y is negative 8. So let's just say that's about here down the bottom. When x is negative 1, y is negative 1. When x is negative a half, y is negative 1 over 8. So that's going to be about there probably. 0, 0. So this is our x and y intercept as well. And we get when x is a half, y is 1 over 8. We get this one here, 1, 1, and 2, 8. So that's kind of way up here again. So you can kind of see how this graph is going to play out. But if I connect all the dots I've drawn, trying to draw, remember with these ones, a nice continuous curve that passes through all of the points. So I'll make these points bigger so you can see it passing through. And this will continue up in this direction and down in the other direction as well. So here I have a cubic, y equals x cubed. Now we're not going to be transforming these functions just yet. That will come later. We are just getting a feel for what the most basic cubic looks like, for example. What the most basic y equals root of x looks like. So moving on. We have the fourth power of x. So we call these quartics. So looking in, we're going to substitute and get a feel for how this graph looks. When x is negative 2, y is positive 16. When x is negative 1, y is 1. When x is negative a half, y is 1 over 16. We get 0, 0. When x is positive a half, we get 1 over 16 again. And we get 1 and 16 over here. So you can kind of, just by looking at the points, you can kind of get a general idea of the shape. But when x is -2, y is 16. So obviously this isn't being drawn to scale, but this is going to be really high up here. When x is -1, y is 1. And when x is -1/2, y is 1/16. So that's going to be like way down here, very, very close to here. We have 0, 0. We have this point here. And then it continues to go up. So we can basically, just by looking at it, it kind of resembles our parabola a little bit, but it goes up way quicker. And you can see once I draw it, down the bottom, once we get through, this looks like it almost touches the bottom. It looks really, really kind of flat down the bottom. So it represents, well, it behaves kind of similarly to a parabola in the sense that it starts off positive. The domain here, the range, I should say, all the y values are positive. It just kind of looks like a steeper parabola at the top and it's a bit fatter on the bottom. Now, all even powers, so think y to the power of 6, y to the power of 8, you will notice these look similar. Now, there's a reason for this, which we will talk about later on. But we're just getting a general idea of how this graph behaves. So we have y equals x to the power of 4. Next one, we're not going to do a table of values because we have talked about this before on the channel. We are looking at a circle. So a circle, remember the equation of it is x squared plus y squared equals to the radius squared. Now this follows Pythagoras' theorem. We've talked about this previously. So if we pick a point basically here and we draw in a dotted line here, we will notice it makes a right angle triangle that obeys Pythagoras' theorem, where some arbitrary value x, let's call this point P, with the coordinates x, y, and the radius is always the same anywhere we go. So everywhere along this circle, we can construct a right angle triangle that follows Pythagoras' theorem, which is x squared plus y squared, or a squared plus b squared, equals c squared, where c is the hypotenuse. So it resembles Pythagoras' theorem. And our circle will always look like this, and depending on the r value, the radius will get bigger or smaller. So here I've made the radius, I've got the y coordinate r, negative r here, positive r, negative r. These are just the x and y coordinates. Here the radius is 4. But this will look different depending on how big the circle is, depending on the radius. But this is generally how we can always draw circles before we apply any transformations. Now, last thing I've got here is that when you rearrange the equation of a circle, so I've written the steps here already. You have x squared plus y squared equals to the radius squared. If I move the x squared to the other side and make y the subject, you will notice that y equals to plus or minus the square root of r squared minus x squared. Now, each of these two separate solutions that I have, y equals the positive root of r squared minus x squared, or y equals the negative root of r squared minus x squared, these create basically two halves of our full circle that we've talked about on the previous page. So this is actually the equation of a semicircle. Now, in the positive case, we just have the half circle in the positive section of the y-axis. So all my y values, all my outputs are positive. That makes sense for here because no matter what I put in the square root, I will get a positive output. And here I get negative outputs. So this is why I have a semicircle that's been reflected on the bottom half of my Cartesian plane. So it's only having the negative outputs of y. So this is how we can graph the basic functions in this section with our powers, polynomials, and circles. And we will move on to some other graphs in the next video. That brings us to the end of this one today. Thank you so much for watching, and I'll see you next time.